In this video, we will talk about hydrogen halide reactions with alkenes. So let's start off by drawing an alkene, and we can just put our double bond right here. We can react this with hydrochloric acid. And so we will just show electron pushing. And by the way, pi bonds serve as good nucleophiles because they have a pair of electrons built inside of them, very similar to that of lone pairs. So next we should have this, where now we have two hydrogens on this carbon and a carbocation on this tertiary carbon. So keep in mind this carbocation went to this tertiary carbon instead of this secondary carbon simply due to a tertiary carbon being more stable than a secondary carbon. And you can look further into that if you read about hyperconjugation. And hyperconjugation simply explains how a tertiary carbon is more stable than a secondary carbon, and a secondary carbon is more stable than a primary carbon. So I just wanted to mention that briefly. Now we still have chlorine with a negative charge floating around in solution. And we can show electron pushing again, with our chlorine being our nucleophile and our tertiary carbon being our electrophile. So now let's move to the next step. So next we should have something that looks like this, with the chlorine atom attached to it now. So the next step is to assign stereochemistry. So what we need to do is look for a chiral carbon and make an R or S configuration, and from that we can possibly show an enantiomer as well, but either way, with an R or S configuration we should be able to show stereochemistry. So the first thing we need to do is look for different substituents. Make sure our chiral carbon has different substituents. So we can trace this bond moving around for verification, and we can trace this bond moving around. And as you can see, these two substituents now are going to be the same. So if they are the same, we are not going to have a chiral carbon, and if we do not have a chiral carbon, we are not going to be able to show stereochemistry. So we can keep this molecule as is. So now let's move to another problem where that may not be the case. So if I have something where my alkene looks like this, and I react it with, we'll just say, a hydrogen with a positive charge and water. And by the way, whenever we show an initial chemical reaction with hydrogen rather than, say, with bromination or with oxymercuration, demercuration, whenever we simply show a hydrogen atom, we are not going to have or demonstrate a bridged species. And if we don't have a bridged species, we will show carbocation formation. And that, as I mentioned earlier, was in contrast to oxymercuration, demercuration, and bromination, because both of those reactions have bridged species, and with that bridge, it prevents a carbocation from occurring. So I wanted to throw that out there briefly. So once again, let's show electron pushing, and our pi bond is going to serve as our nucleophile. So next we will have this, where we have 3 hydrogens attached to this carbon now instead of 2. And we will have a carbocation on this secondary carbon. Now keep in mind we will have 2 products from this, because remember, a secondary carbocation is less stable than a tertiary carbocation, so we could also have this product as well, where we show a carbocation on this tertiary carbon instead of the secondary carbon. And when that happens, the secondary carbon will have two hydrogens. And so a question might arise, well, where did that hydrogen come from? Because in the previous product, we only had one hydrogen, which was implied right here. Well, it came from this implied hydrogen, and a hydride shift occurred, and that's what it's called, a hydride shift. So what is a hydride shift? Well, a hydride shift is when, say for example, this hydrogen moves to this secondary carbon, and the carbocation moves from the secondary carbon to the tertiary carbon, which is where it's more stable. So that's where that happened, and so now let's talk about our nucleophilic attacks. So remember, we still have water in solution. So we are going to show a nucleophilic attack from water onto the carbocation. And you know, sometimes students will have questions, and those questions will relate to how a nucleophile is able to attack a secondary carbocation when a tertiary carbocation is more favorable. Well, through kinetics, and I suppose this will be the short answer, but through kinetics, a nucleophile sometimes is able to attack a secondary carbocation due to its close proximity before a carbocation has the ability to rearrange or go through a hydride shift, as demonstrated in this example. So if that happens, you'll end up with something like this, but another thing to mention too is that you will end up with a minor product, because that is less stable. And over here with the tertiary carbon, you'll end up with a major product because it's more stable. And so now let's continue with this reaction and show the next step. So now over here we are going to have water attached. And by the way, when water attaches itself to this carbocation, it actually looks like this at first, with a positive charge. But since we are in aqueous solution, eventually one of those hydrogens just gets plucked off, and there's no need to worry about it anymore because you end up with an alcohol anyway. But I just wanted to show that that does occur. So now we can get rid of that. And so the next question is, well, can I assign stereochemistry? And by the way, remember, this is an implied hydrogen right here. Well, it looks like we will be able to do that because we have 4 different substituents attached to this carbon. So let's go ahead and assign priorities. So we can start it off with 1, 2, 3, and 4, in which case we will move in this direction. And we can just simply be creative with our wedges and our dashes, because remember, this reaction is just taking place randomly, and for convenience we could just make our wedges and dashes however we like in the first product. So for this, we will say that this is wedged, and we will make our lowest priority group dashed for convenience. So now that we see that, we can show that we are working with an S configuration. So now let's demonstrate the R configuration of this, which would be an enantiomer. And that's going to be easy to do because all we have to do is just interchange our wedges and our dashes. So instead of alcohol showing a wedge, now we can show an alcohol with a dash. And instead of hydrogen with a dash, we can show that now with a wedge. And so once again, we will just assign priorities for verification. So we move in this direction. We end up with an S configuration, but our lowest priority group is now pointing toward us rather than away, so we invert, and we end up with an R configuration. So those are the enantiomers that we could make, and as I've mentioned before, that also demonstrates stereochemistry. So now let's go into our major product and continue this process. So as shown before, our water is our nucleophile. And we will see a nucleophilic attack on the carbocation. And our next step will look like this. So now we want to ask ourselves, okay, well, can we show stereochemistry? And to do that, we need an RS configuration. So to begin, we need to make sure that all of our substituents are different, and we can immediately see that we have two methyl groups. And since we have two methyl groups, we are not going to show stereochemistry because we are unable to establish an RRS configuration. So we can just keep this product as is, and there's no need for further elaboration. But one thing I also want to mention briefly is I want to talk about carbocations and why we are able to show enantiomers and how that works exactly with a carbocation. So if I were to, say for example, show a molecule with a tetrahedral geometry, and I'll just use this as R1, we'll assign this as R2, R3, and R4. And these R groups are just carbon chains of some sort, so it really doesn't matter what they are. But let's just assume that one of those gets knocked off, and we'll say that R4 gets knocked off and forms a carbocation. So we end up with R1, R2, and R3 with our carbocation. Well, what happened was we went from a tetrahedral geometry into a trigonal planar geometry. Or we went from sp3 hybridized to sp2 hybridized. And when that happened, we ended up with a flat molecule. And when we have a flat molecule, as demonstrated with the carbocation, we can have a nucleophilic attack from either side of the molecule. And to me that's analogous to a coin in which is sp2 hybridized, because when you flip that coin, the coin is flat, but when you flip that coin, you end up with or you should theoretically end up with 50% heads and 50% tails. And that is how we are able to show that we get a mixture of anti plus syn addition. Addition because we are working with an addition reaction. And that also suggests that we do not have stereoselectivity or specificity. Because we have both anti and syn addition due to that carbocation being able to serve as an electrophile from either direction of the flat molecule. And so that is why we end up with syn and anti addition.